my beautiful students, I know your Q2 examination is knocking the door. So at this moment you are looking for the most expected question that you are going to face in your examination. So yes, here I am going to cover the entire inorganic chemistry part that will include the D and F block elements and the coordination compounds. So all probable problems, MCQs that I am going to cover here. So without delay, let's get started with the first chapter, that is D and F block elements. So yes, here we will discuss a little bit model paper at first. So all the model paper, whatever the question came from the D and F block, we are going to cover at first, and then a little bit from the question bank, whatever the previous year question and a little bit important question, that also we are going to cover. So if you do this, I am assuring you it's going to be more than enough. So let's proceed. First question here you can see, which of the following element is liquid at normal temperature? So that is mercury. So go through the question properly. See, we have a tendency to mark water, right? But water is not an element, it's a compound. So this is mercury. Proceed. Okay, so here it's a very important MCQ actually. We are having the transition metal compounds and they are used as a catalyst. So V2O5, it is used for the contact process, that is B. Nickel is used for the hydrogenation, PDCl2 is used for the Wakers process, and this is the Ziegler-Natta catalyst, it's used for the manufacture of polythene. So CADB, option A is going to be the correct one. Next, let's proceed. What are transition elements? Give an example. So as you can see, elements having partially filled d orbitals either in their ground state or in their common oxidation state. Okay, they are called as transition element. You can take the example of manganese. Okay, so let's proceed further. What is Lanthanoid contraction? Mention two consequences of it. That is basically gradual decrease in the atomic and ionic radii from lanthanum to lutetium. Right. So what are the consequences? The consequences you can include that it becomes very much difficult to separate the elements of 3D and 4D. So like zirconium and hafnium, from their ore it becomes difficult to separate zirconium and hafnium because of the same chemical and physical properties, right? Another one you can take, the basicity decreases from lanthanum to lutetium. Okay, let's proceed. Okay, so complete the equation. I can do it like chromite, right? 4FeCr2O4. That is chromite. Next here MnO2, if it is fused with KOH, I will get K2MnO4. K2MnO4, along with that definitely 2H2 I will get. Okay, now KMnO4, if it is decomposed, means if it is, you can see thermal decomposition, heat is given here, K2MnO4, along with that MnO2 you will get, and oxygen. Okay, let's proceed. Statement. Potassium permanganate is a powerful oxidant. Yes, that's correct. KMnO4 oxidizes I- to IO3- in acidic solution. So that's going to be a wrong one. Why? Because it oxidizes I- to I2 in acidic, but in alkaline and in neutral medium it oxidizes I- to IO3-. In acidic medium it oxidizes I- to I2. Okay, so statement 1 is correct, but statement 2 is incorrect. Let's proceed. Electronic configuration of the transition metal X is +3, oxidation state is 3d5. Then what is the atomic number? So if it is 3d5, then if you include 3 more electron, it will be 3d6 and 4s2. So 3d6, 4s2 is representing 26, that is nothing but iron. Right? So option C is the correct one. Let's proceed. Give reason. Separation of lanthanides is difficult from their natural occurrence. Here I already told you, due to the lanthanide contraction, the atomic radii of zirconium and hafnium, it becomes almost similar. Okay, so they occur together. Okay, next, study of actinides are difficult. Why? Because first of all they are radioactive element. Next, their half-life are very short. Okay, so like you need more time to do the research on it, right? Next one is like they could be prepared in nanograms. right? So these are the things for what actinoids study is difficult. Let's proceed. Explain the preparation of potassium permanganate from MnO2 with balanced equation. Okay, so this is the potassium permanganate preparation. It's a very important, either dichromate or potassium permanganate preparation you can expect in your examination. Okay, so here what we will do, first we will fuse MnO2 with KOH, we will get K2MnO4. After that conversion, means it's a disproportionation type of reaction takes place. K2MnO4 will give you KMnO4 plus MnO2. Okay, so this is how you can get. Next, mention the gas evolved when KMnO4 is heated. So KMnO4, we already did this in the form of fill in the blanks. Here again, KMnO4, if it is heated, you will get K2MnO4 plus MnO2 plus oxygen gas. Okay, let's proceed. Considering the elements of 3D transition series, write the element which is first unable to form monoxide, that is scandium. Scandium is unable to form the monoxide because it always exists in +3 oxidation state. Next, having positive E0 value, that is copper plus 0.34 something. Okay. Next, a base element of Ziegler-Natta catalyst, that is Ti. Okay, Ti means titanium. Proceed. Okay, this is a common oxidation state shown by the element with atomic number 21, that is +3. Let's proceed. With respect to first transition element series, which element has highest second ionization enthalpy and lowest enthalpy of atomization? So definitely first answer is going to be copper. Why? Because copper, if you remove the first electron, 4s1 will be removed and it is having 3d10. So from 3d10, second electron removal becomes very difficult. So that's why second ionization enthalpy become high, and lowest enthalpy of atomization is because it is having zinc. Why? Because zinc has no unpaired electron, all the electrons are paired up, that's why. Let's proceed. Write the balanced chemical equation involved in the manufacture of potassium dichromate from the chromite ore. So first, as you know, you just have to heat FeCl2O4, that is a chromite, with Na2CO3. You will get sodium chromate. Sodium chromate on being treated with acid, you will get sodium dichromate. Sodium dichromate, you have to treat this with KCl. You will get K2Cr2O7. Let's proceed. Write the formula of the 3 different types of compounds formed when lanthanide reacts with carbon or heated with carbon. Okay, so we can get Ln3C, Ln2C3 and Lnc2 type of compounds. Okay, let's proceed. Okay, this is from the question bank we are going to cover. Here, name the 3D series elements having maximum melting point and minimum melting point. Maximum melting point will be having chromium because of the presence of unpaired electron, and minimum is zinc because it has no unpaired electron. Proceed. Why do the transition element exhibit high enthalpies of atomization? So the reason is the number of unpaired electron. Okay, they have stronger interatomic interaction because of the presence of unpaired electron. As a result, their enthalpy of atomization, means to separate them into the individual atom, becomes very difficult. Let's proceed. The atomic sizes of iron, cobalt, nickel are nearly same. Why? Because iron, cobalt and nickel, their like increasing effective nuclear charge and poor shielding effect, they balance each other properly. Okay, that's the reason as you are moving from iron, nickel, definitely the nucleus will gain proton, nuclear pool will increase, but in the D shell the electrons will also be added, right? So they will counterbalance each other, and as a result of this, atomic radius becomes constant. Okay, let's proceed. Why manganese exhibit maximum oxidation of +7 only with oxide? So it's a very important question. So oxygen can form a very strong multiple bond with manganese. Okay, p-pi d-pi type of bonding they can form, that makes the entire compound very stable. Okay, so but here fluorine cannot make it. Just because it cannot stabilize the +7 oxidation state with the single bond only, right? That's the reason oxygen can do it. Proceed. Cu2 plus is more stable than that of Cu plus, because Cu2 plus has it's all about the hydration ionization enthalpy. Okay, so the stability of Cu2 plus is more due to the much more negative hydration enthalpy. Whenever you are just dissolving that Cu2 plus into the water, the hydration enthalpy of Cu2 plus is more than that of Cu plus. Okay, so that compensate the ionization energy that is required to remove one electron from 3d10. Okay, that's the reason Cu2 plus is more stable. Let's proceed. Why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? So Cr2 plus is reducing because the configuration changes from D4 to D3, but Mn3 plus is oxidizing because the configuration changes from Mn3 plus to Mn2 plus, that is D5 configuration, right, which has some half-filled stability, right. D3 has no stability, but D5 has extraordinarily symmetrical stability, right. Proceed. The E0 of M2 plus M value for the copper is positive. The reason, okay, so the reason is high enthalpy of atomization and low enthalpy of hydration. Okay, means a large amount of energy is required to convert the solid copper to Cu2 plus ion, right, and this particular thing will be counterbalanced by the hydration. Okay, so I guess you understood this. First of all, Cu2 plus ion needs to be prepared, right, and after that Cu2 plus needs to be stabilized. So how it will be stabilized? By adding the extra hydration enthalpy. So this much energy you need, that's why plus 0.34. Let's proceed. Which is a stronger reducing agent, Cr2 plus or Fe2 plus, and why? Definitely Cr2 plus is going to be a very stronger reducing agent than that of Fe2 plus. Why? Because the configuration you see for Cr2 plus, it is changing from D4 to D3, okay, and D3 is getting stability because it is half-filled T2G orbital. Okay, T2G can have 6 electron maximum, so it is half-filled T2G and hence it's more stable. Okay, let's proceed. Transition elements form colored compound. Give two reasons. First, it is a DD transition that I already explained. So unpaired electron should be there and partially filled d orbital should be there. It will undergo DD transition, right. As a result of this, you will see it will radiate the complementary color. Okay, proceed. The transition metals and their compounds are known for their catalytic activity. Give two reasons. First reason is variable oxidation state. So many oxidation state they are having. Next, surface area. They provide a large surface area for the adsorption of the reactant molecule. Next, the presence of incompletely filled d orbital. It's very important. Okay. Next, it can form very stable intermediate compound. Okay, like vanadium pentoxide we can use in the contact process for the manufacture of H2SO4 just because of that. Okay, let's proceed. Okay, iron catalyzes the reaction between iodide and persulfate ions in the reaction. Explain the catalytic action. Okay, so here you can see if you just look at the reaction, you will understand iron 3 plus will at first react with I minus, okay, and it will form iron 2 plus and it will liberate I2. Further, this iron 2 plus will react with persulfate to give you the SO4 2 minus and iron 3 plus will be regenerated. So if you just look at the reaction, then you will understand. Okay, I guess it's clear. Let's proceed. Write the characteristics of the interstitial compounds. So interstitial compounds definitely they have very high melting points. Okay, they are chemically inert. They retain their metallic conductivity. Okay, proceed. What is the composition of mismetal and write one use of it. So this is the composition. 95% lanthanoid should be there. Plus iron should be there almost 5% and the trace of sulfur, carbon, these things should be there. Okay, and mismetal is used in magnesium based alloy to produce bullets. Okay, shell and lighter flints. Okay, let's proceed. Draw the structure of dichromate ion. What is the value of bond angle in CrOCr? So this is a structure of dichromate ion. You can see the bond angle is 126 degree. Let's proceed. Give general characteristics of lanthanides. Okay, 3-marker question. It's definitely a white metal, tarnished, and definitely it gets tarnished in air rapidly. Hardness increases with the atomic number. Next, they are good conductors of heat and electricity, and all lanthanide ion except La3+ and Lu3+, they are colored, both in solid state and in aqueous state as well. Okay, so I guess one more. Okay, lanthanide ion except F0 and F14 type, they are all paramagnetic. Clear? Proceed further. Okay, what is actinoid contraction? Actinoids show greater number of oxidation state and why? Okay, one by one let's discuss. First, actinoid contraction is same as that of the lanthanide contraction, gradual decrease in the size of the atoms of actinides across the series. Okay, and next question, actinoids show greater number of oxidation state. Why? This is because the energy gap between 5F60 and one more 7S. Okay, comparable energies, very close by there. Okay, so removal of electrons are easy, that's why they show variable oxidation state, even more than that of lanthanoids. Last question, common oxidation state, it is +3. Let's proceed. Why cerium shows +4 oxidation state? Okay, so basically cerium shows +4 oxidation state. If you see the electronic configuration, then you will understand. Cerium +4 will get the xenon-like configuration, that's a noble gas. So to get the inert gas-like configuration, it shows +4 as an better oxidation state, best. Okay, next, what is the highest oxidation state shown by the actinoids? That is +7 can be exhibited, and name an element that shows highest oxidation number among the actinoids. Neptunium is one of the element that will show +7 oxidation state. Okay, let's proceed. Give any 3 general characteristics of actinoids. Here you can see definitely all of them are radioactive, silver color, highly reactive, okay, and paramagnetic in nature. What we can tell more? Slightly affected by the concentrated nitric acid owing to the formation of the protective oxide layers. Okay, so that is basically creates some passivity, right? And it can be highly affected by the hydrochloric acid. And oxocation they used to form, as you can see, neptunium with oxygen, NPO+, it is oxocation. Okay, so I guess it's clear to you. Let's proceed. Lanthanides and actinoids difference you can just go through from here, and you can just pick any 3 of them and you can just write it down. Okay, proceed. Study of actinoid element is difficult. Give 3 reasons. So first, I already told you, radioactive element half-life is very short and they can be prepared in nanograms. Let's proceed. Okay, so let's proceed further. Okay, so here we are ending for the D and F block element and we are entering into the coordination compounds. So yes, let's proceed. So here comes the first question. What type of bond is L to M in coordination in complex compound? That is coordinate covalent type of bond. Let's proceed. If the secondary valency of COCl3 4NH3 is 6, the solution conductivity in silver nitrate corresponds to, okay, let me draw the compound at first. So CO, let's take NH3 whole 4 Cl2. So you can see secondary valency is coming 6. So outside there will be 1 Cl. So if now it dissociates, it will form CO NH3 whole 4 Cl2 plus Cl minus. So it is an 1:1 electrolyte. Let's proceed. Given that 1 mole of NiCl2 6H2O with excess AgNO3 precipitates 2 moles of AgCl. What's the secondary valency of nickel? So if I draw the structure, then NiH2O whole 6. See, secondary valency is 6 because 2Cl needs to be outside to give 2 moles of AgCl precipitation. So, secondary valency is coming 6, right. Let us proceed. What is the sum of the oxidation number of the cobalt in this 2? Okay. So, for the first case, let me just take it as X plus for water it will be 0, for Cn minus it will be -1, for ethylene diamine also it is going to be 0 equals to +2, right. So, for this case if I solve then X will be +3. Okay. For this case let me just calculate, let us take it as Y plus 2 into -1 for bromine plus 2 into 0 is equals to +1, right. So, for this case Y is coming +3. So, +3 plus 3 +6. Let us proceed. What is the primary valency of iron in the coordination entity of this compound? Okay, I have to dissociate this compound at first. The compound is Fe4 FeCN6 FeCN6 whole thrice, right. So, now if I just break it down it will be something 4 Fe3 plus 3 FeCN whole 6 4 minus, right. This is how I can break it down. Now, from this compound I can just find out the oxidation state. So, iron let us take it as X plus 6 into -1 for cyanide equals to -4. If you solve, X is coming as +2. So, oxidation number will be satisfied by the primary valency, +2 is going to be the answer. Clear? Let us proceed. Which of the following compound has enantiomer? So, enantiomer, to get the enantiomer you must need octahedral complex and that must be chiral. So, your option B is going to be the correct option. It is octahedral as well and it is chiral. No plane of symmetry will be passed through it. Next, linkage isomerism is is observed in ambidentate. Okay. Next, the compound this and this are what type of isomer? Okay. So, here you can see the ions. Okay. So, ions are different. Okay. So, ionization isomers. Let us proceed. Which of the following orbitals does not belong to T2G? So, this is dz square. Okay. So, dz square does not belong to T2G, it is a part of EG. Let us proceed. What will be the electronic configuration of D5 in term of T2G and EG if the octahedral filled when delta O splitting energy is less than P, pairing energy is more than delta O. Okay, let me just draw this for you. So, if it is breaks down EG and this is my T2G, right. So, 5 electron, right, 1, 2, 3. Now, 4th electron where it will go. So, they are saying delta O is less than pairing energy, means pairing will take place later rather than it will go to the EG part. So, 4, 5, right. So, T2G3, EG2. Okay. Let us proceed. State the postulate of Werner's coordination theory. You can see, you can just talk about the primary and secondary valency, which one is ionizable, what does it mean by secondary valency, that ligand used to satisfy that. Then you can mention about the the ions group that bound by the secondary linkages, they have some special arrangement within it. Okay, there's many points you can mention. Let's proceed. FeSO4 solution mixed with NH4 whole twice SO4 solution is 1:1 molar ratio gives the test for Fe2 plus, but CuSO4 solution mixed with aqueous ammonia in 1:4 molar ratio does not give the test for CO2 plus, because for the first case it forms the more salt. Okay, more salt when it dissociates it gives the test for the Fe2 plus because it dissociates Fe2 plus. Okay, but whenever CuSO4 is mixed with the solution, aqueous ammonia solution in 1:4, it makes a coordination compound and Cu becomes a part of the coordination entity. That's why it is non-dissociable. So, it doesn't give the test for CO2 plus. You can just go through this. That's the thing I just told now. Okay. So, this is the reason. Okay, let's proceed further. Okay, on the basis of the following observation made with aqueous solution, assign the secondary valencies to the metal. Okay, so one by one we will do. For the first case, number 1, here let me write number 1. Here I am getting 2 AgCl unit as a precipitation, means the compound should look like PD NH3 whole 4 outside Cl2, and here I will write the secondary valency. Okay, secondary valency for the first case is going to be 4. Second case, if I draw it, you can see I am getting 2 unit of AgCl precipitation. So Ni H2O whole 6 outside Cl2. This case it is 6 secondary valency. For 3 there is no AgCl precipitation, right? So you can do it like PtCl4 like this. Okay, dot HCl. Okay, so for this case 2 HCl, I am getting 4, right, secondary valency. Next COCl3, I am getting 1 as a AgCl. Okay, so CO here NH3 4 inside 2 Cl outside 1 Cl. So for this case also I am getting 6. Next, okay, I am getting no AgCl precipitation for 5. So PT, here I am having NH3 whole twice Cl2, right? No precipitation, and hence you are getting here 4 as well. Okay, I guess this is clear to you. Let's proceed further. Explain the example of the following. Okay, so coordination entity, ligand, and coordination number. Coordination entity means whenever the metal is connected to the ligand with the coordination bond, right, and that part is non-ionizable. Okay, and this is you can explain as coordination entity. Next is ligand. Ligand is basically electronically enriched species that donates the electron pair to the metal center. Next, coordination number. Coordination number is the number of ligands that is attached with the metal. Okay, so you can see here comes the full explanation of this. You can just go through. Let's proceed. Okay, let's proceed. Explain with 2 examples each of the following coordination polyhedron. What is coordination polyhedron? It is basically the special arrangement that ligands around the central atom. Okay, this is called coordination polyhedron. Okay, you can just take the example of, let's say, nickel tetracarbonyl compound. Okay, next you can see homoleptic complex. If in the coordination entity you are having same type of ligand, it is called homoleptic complex. Next is heteroleptic complex. If you in the coordination entity you are having 2 different type of ligand, then you can just call it heteroleptic complex. Examples are given here. Okay, let's proceed. What is meant by unidentate, bidentate and ambidentate ligands? Give 2 examples. So unidentate ligand means it has only one donor atom to form only one coordinate bond, like Cl minus NH3, like this. Bidentate means it has 2 donor atom, okay, like oxalate. Okay, next ambidentate, it has ambidentate, it has 2 donor side but donates from one side at a time. Okay, like Cn minus, I can take the example, SCN minus, I can take the example. It has 2 donor side but it donates from one end at a time. Okay, let's proceed. What are chelating ligands? So chelating ligands, you can see when a di or polydentate ligands, they uses 2 or more more than 2 its donor sites to simultaneously to catch only one metal, to bind with a single metal. Okay, it is called a chelate ligand. Okay, so EDTA is one of the example of it. Let's proceed. Okay, specify the oxidation number. Let's do one by one. For the first, number 1 we will do first. Okay, so For cobalt we will take as X, for water it is 0, for cyanide it is -1, for ethylene diamine again it is 0 equals to +2. So X value is becoming +3. Okay, number 2 PTCl4 2 minus. Okay, so here you can see X plus for the chlorine -1, so -1 into 4 equals to -2, hence I am getting X equals to +2, right. Next, number 3, X for chromium, ammonia it's going to be 0, plus 3 into -1 for chlorine equals to 0, right. So X is going to be +3. Next, for cobalt let's take X plus for bromine -1 into 2, ethylene diamine 0 equals to +1. So X is going to be +3. That's it. Okay, I guess it's clear to you. Let's proceed. Okay, using the IUPAC norms, write the formulas for the following. One by one we will write. First one, you can see tetrahydroxidozincate 2. Okay, so Zn with OH whole 4. So zinc oxidation state must be +2, right? So here I will be having 2 minus, right? Next, hexaamine cobalt 3 sulfate. Okay, so cobalt with hexaamine means 6 ammonia. Okay, and sulfate 3 sulfate is so 4 3. Okay, by default oxidation number will come as 3. Okay, next let's proceed. Wait, this sulfate will go outside. Okay, let's proceed with the third one, that is potassium tetrachloridopalladate 2. Okay, so potassium is cation here, so K2 tetrachloridopalladate, so PD with 4Cl. Okay, that's it. Next, fourth one, potassium trioxalatochromate 3. Potassium chromate 3 means oxidation state must be 3, so K3 Cr trioxalato C2O4 whole thrice. Okay, now chromium also oxidation state 3. 5, diamine dichloridoplatinum 2. Okay, so diamine dichlorinum platinum. Okay, platinum, then diamine dichloride. Okay, I guess this is clear to you. These are the from the IUPAC norms, these are the formulas. Let's proceed further. Using the IUPAC norms, write the systematic names. So just opposite we have to do, we have to write the IUPAC name. CONH3 whole 6 Cl3. Okay, so this is going to be hexaamine cobalt, no space should be there, cobalt, here oxidation state will come 3, then chloride, right. Next one, CONH3 whole 4 ClNO2 then Cl. Okay, so amine we will start with because alphabetically it comes first. How many amine? Tetraamine. So tetraamine, then chlorido, then nitrito. So nitrito is an ambidentate ligand, it is binding from the nitrate end, nitrogen end. So you have to write nitrito N, then you have to finish with cobalt. Here oxidation state will come as 2, 3. Here oxidation state will come as 3. Okay, then you have to end with the anionic part, that is chloride. Okay, let's proceed with the third one. Okay, hexaamine nickel. Hexaamine nickel. Okay, here oxidation state will come 2. Then chloride. That's it. Okay, I guess this is clear to you. Let's proceed further. Explain the geometrical isomerism in CN4 with examples. Okay, so here you can see whenever you are having MX2 L2 type of thing, you can have cis and trans isomer. Okay, they will be opposite to each other. Okay, and other square planar like MABXL, all the 4 ligands are different. For those case also 3 different isomer you will get, 2 cis and 1 trans. Okay, let's proceed further. Why geometrical isomerism is not possible in tetrahedral complex? Because it do not show because of the relative position in the of the unidentate ligands. Okay, they are like the way it attached with the metal in a spatial, in a 3D geometry, it will not show any kind of geometrical arrangement. Okay, I guess it's okay. Let's proceed. What do you mean by optical isomerism? Optical isomerism means they will have the mirror image. Okay, they cannot be superimposable, non-superimposable mirror image. Okay, these are called enantiomers. Okay, so next, they are also called as the chiral compound. Okay, and you can tell that the 2 forms are called dextro and levo. Okay, and they rotate, they can rotate the plane of polarized light in the polarimeter. Okay, if it rotates the right to the right, then you can call it dextro. If it rotates the light, plane of polarized light to the left, then you can call it levo. That's it. Next, let's proceed with the next question. Draw the optical isomers of this. Okay, let's draw it. So platinum with 2 chlorine and ethylene diamine, right? Okay, so you can draw it in this way. Optical isomers only we have to draw. So 2 chlorine I am placing on the same plane. Cis we will draw. Okay, this can be your 1 ethylene diamine and this can be your 1 ethylene diamine. Okay, now place one mirror. Okay, and draw the mirror image. Platinum, here Cl, here Cl, here 1 ethylene diamine and here 1 ethylene diamine. If it is your dextro, then it is your levo. Okay, this is how you should draw it. Next, okay, cobalt with 3 ethylene diamine. So let's draw it. So cobalt, so we can place 1 ethylene diamine like that, 1 like this on the plane, 1 like this. Now you can draw the mirror image of it. Okay, CO, here I can place 1 here, I can place 1 here, and I can place on the plane itself. Okay, so here also you can get 1 D, another 1 L. Okay, I guess these are clear to you. Next, out of this following 2 coordination entities, which is chiral? Okay, so for this particular case we have to check for the cis one. Cis is optically active one. So if I just draw the structure for you, you can see for cis only I will draw chromium, 2 chlorine on the plane, oxalate we can draw like this because these are bidentate. Now you can draw the mirror image. chromium, here chlorine, and here oxalato, like this. Okay, one D, another one is L, like that you can represent. Okay, so here if you just draw the trans, if you just for your reference I am telling, this is your cis isomer. Okay, this is your cis. In case if you want to draw the trans, you will see the plane of symmetry pass through it. Let me just show you once. Here let's say in the plane oxalate is there, and above I am having chlorine. So here you can see this is the plane of symmetry. This is the plane of symmetry. Okay, as a result of this is your trans, right? Trans is not optically active. Okay, this is not optically active. I guess this is clear to you. Let's proceed further. Explain linkage isomerism. So linkage isomerism arises in a coordination compound containing ambidentate ligand. Here you can see for this particular compound nitrogen end is binding. If I want to write the isomer, then it will be something like this, ONO-Cl2, right? Let's proceed. Ionization isomerism. So it happens because of the presence of the counter ion. Once it is placed in the inside the coordination entity, another time it is outside. You can see the example, once sulfate is inside the coordination entity and here it is outside, bromine is inside, like that. Let's proceed. Solvation, it's a number of water that is present inside the coordination entity and outside. Here you can see only 6, all the 6 H2O inside, this is violet, but here for this case 1 H2O outside, it is grey green. Okay, let's proceed. Explain the coordination isomerism. Coordination isomerism, this arises because of the interchange of the ligand between the cationic and anionic entities. You can see here the ligands, here NH3, here CN. If I just alter them, CN and NH3, then I will get the coordination isomerism. Let's proceed. Explain VBT. Here you can see this is the entire VBT explanation. There is a hybridization of N-1D, NS, NP. This orbital hybridization takes place, overlap of this orbital takes place and their energy becomes equivalent. Okay, so they can form octahedral compounds, they can form tetrahedral compounds. Okay, so that's it. Okay, so this is all about the VBT. Let's proceed. Here we have to explain the hybridization, magnetic property and geometry. So cobalt 3+ here, cobalt 3+ is basically 3d6 geometry, right? So if I just draw the 3d6 one, I am having also 4s, I am having 4p as well. This is my 3d, this is my 4s, this is my 4p. So it will be looking something like 1, 2, 3, 4, 5, 6, like that. Okay, so now what I have to do, once the ammonia will approach near to the cobalt center, then what will happen? Force pairing will take place against the Hund's rule. Why? Because ammonia is a strong field ligand. So if force pair takes place, this will be paired up here, this will go there. Okay, so let's just do it. 1, 2, 3, 4, 5, 6. Okay, and these orbitals will be there. So now hybridization will take place along with this 1s and 3p. So D2 sp3, this is the hybridization. And now here in this hybrid orbital, once it is made, it will be looking something like this. Wait, 1, 2, 1s, 3p. Okay, so all the ammonia will donate their lone pair here. Okay, so this is how. So overall geometry is coming as D2 sp3. Now if you just ask about the magnetic property, no unpaired electron, right? Here all the electrons are paired up, so I can say it is a diamagnetic compound. Okay, diamagnetic in nature. I guess it is clear to you. Let's proceed. Okay, geometry. Geometry also, for this case I will be having octahedral geometry. One more information I want to share. Octahedral geometry, strong field ligand, inner d orbital taking part in the hybridization. You can also call it as inner orbital complex. Okay, let's proceed further. Give 3 limitations of valence bond theory. So it involves a number of assumptions. It does not give the quantitative interpretation about the magnetic data. Like it does not explain the color, why the color comes in coordination compound. Then this type of thing you can give actually. It does not distinguish between weak field and strong field ligand. Any 3 you can give out of it. Next, explains CFT, crystal field theory. So basically it's an electrostatic model which considers the metal ligand bond is ionic. Means electrostatic interaction we have to consider. Metal is a point positive charge, ligand is a point negative charge. So at first what happens, the metal and ligand, they comes close to each other because of the Coulombic interaction only. Then what happens, ligand is having its own electron sphere, and metal is basically having its own d orbital electron. So when they come close to each other, splitting takes place, inter-electronic repulsion takes place. As a result of this, d orbital gets splitted. Okay, so 3 orbital, they gets minimum repulsion, their energy becomes below, and 2 orbitals, their energy becomes high, that is Eg, and the orbitals, they are getting lower energy, they are togetherly called as T2G. Okay, so T2G are basically dxy, yz, dzx, and Eg are basically dx square, y square, dz square. That's it. Okay, so I guess it's okay, it's clear. So definitely if you are having a very strong field ligand like Cn minus, CO, okay, this type of ligand if you are having, then the splitting energy will be more than that of the pairing energy. Then during the electronic configuration, while you are just going to fill up the electron, then pairing will take place at first rather than that of going to the Eg level. But if you are using a very weak field ligand like F minus, Cl minus, then pairing energy will be more than that of the splitting energy. In those cases, pairing will take place in T2G, then it will jump to Eg. That's it. Let's proceed. This is the figure for the octahedral splitting. You can see. Let's proceed. It is a tetrahedral, just T2G and Eg. Don't call it Eg or T2G. G term will not be used for the tetrahedral. Only E and T2. Their position will be changed as well. Okay, E will come below, T2 will go up. Okay, let's proceed. What is spectrochemical series? Explain the difference between weak field and strong field ligand. A spectrochemical series is basically the arrangement of the ligands in the increasing order of their crystal field splitting energy. Okay, and next question kya tha? Difference between them. Okay, the ligand that is present in the right hand side, they are strong field ligand, and if they are in the left hand side, they are basically weak field ligand. And definitely strong field ligand, they causes higher splitting in d orbitals, and weak field ligand, they causes lower splitting. Okay, for them pairing energy becomes more. Let's proceed. What is the crystal field splitting energy? How does the magnitude of del O decide the actual configuration of d orbitals in coordination entity? So basically what happens when ligand approaches to the metal center, then d orbital splits in 2 different sets. One is T2G, another one is Eg, right? The energy gap in between these 2 orbital is basically called as crystal field splitting energy. Okay, next, how does the del O decide? Okay, so definitely it depends basically upon the ligand that you are using. If you are using a strong field ligand, then splitting energy will be more than that of the pairing energy, right? Then pairing will take place in T2G, then the electron will go to the Eg, right? Next, if you are using weak field ligand, then splitting energy will be lesser than that of the pairing energy will be more. So the electron will be go to the Eg, then it will come to the pairing. That's it. Let's proceed. This is what it is written here as well. Let's proceed. Okay, CrNH3 6 3+ is paramagnetic, while NiCN 4 2- is diamagnetic. The reason again is the field of the ligand. Cn is a very strong field ligand. As a result of this, it will cause force pairing in the d orbitals of the nickel. As a result of this, you will get no unpaired electron over there. Hence, it will come up to be a diamagnetic. Whereas, if you look for the ammonia, in that case, it will not force pair the electron, right? As a result of this, unpaired electron will be there. You will get paramagnetic character. Okay, I guess it's clear to you. Okay, again the same type of question. This is strong field ligand, this is weak field ligand. Strong field ligand will force pair, right? And you will not get any unpaired electron, hence diamagnetic. Cl, weak field ligand, unpaired electron will be there, no force pairing, right? Hence paramagnetic. Okay, let's proceed. FeH2O 6 3+ is strongly paramagnetic, whereas the same reason you can see because of the unpaired electron. Next, okay, a solution of NiH2O 6 2+ is green, but a solution of NiCN 2- is colorless. So the reason is again the weak, the field of ligand. H2 is a weak field ligand, right? So as a result of this, unpaired electron is present, and unpaired electron means it will undergo D to D transition, right? And hence you will see the color. But whenever it comes to the matter of Cn, for this case what happens? No unpaired electron is present because it will force pair the electrons. Hence there is no D to D transition, hence no color. Okay, proceed. Okay, FeCN 6 4- and FeH2O 6 are different in color in dilute solution. So the reason is basically the same. The color, it definitely depends upon the crystal field energy, right? For FeCN 6, it's a very strong field ligand, right? So as a result of this, higher CFSE value we can expect, right? But for H2O, comparatively lower CFSE value, D to D transition will be different, right? For strong field ligand, CFSE value is more, hence D to D transition will be more, hence you can see color, different color, right? But for H2O, ligand field is low, CFSE value is low, hence D to D transition, it will also differ, right? So different color you will observe. Let's proceed. Explain the violet color of the complex, this on the basis of crystal field theory. Okay, so definitely any crystal, any complex compound, they exhibit color because of the D to D transition. For this particular case, TiH2O 6, like here what happens, light, in case of this, when light corresponding to the energy of blue-green region is absorbed by the complex, it will excite the electron from T2G level to EG level. Okay, so if blue light is absorbed, then its complementary color will be released. So complementary color is basically the violet color. That's why violet color you can see from outside. Okay, let's proceed. Anhydrous CuSO4 is white, but CuSO4 5H2 is blue in color. Again, due to the heating, water molecule evaporates from the crystal of CuSO4 and it becomes anhydrous. Okay, so there is no splitting in that particular case and no DD transition, but that's the reason your anhydrous compound is colorless. Let's proceed. What will be the correct order of the wavelengths of absorption in the visible region? Okay, this is also depends upon the ligand field. NO3- will come first, then NH3, then H2. So for this case also, the correct order of the wavelength of absorption, H2 will come first, then NH3, then NO2. Okay, let's proceed. Discuss the nature of bonding in metal carbonyls. So here comes a synergic type of bonding. So synergic type of bonding, what happens basically, metal carbon bond, usually a sigma bond that takes place in between S and P orbital. Okay, S and P both characters are there. Okay, so what happens basically, carbon at first gives the electron cloud to the metal center and it forms the sigma bond. Further what happens, metal gives the electron cloud back to the carbonyl and it creates some pi character as well. Okay, so it has both sigma and pi character. Okay, so carbonyl accepts the electron cloud in its anti-bonding pi star. Okay, so as a result of this, both sigma and pi character, some back bonding character you will get out of it, that is called synergic bonding. Okay, let's proceed. Aqueous copper sulfate solution gives a green precipitate with aqueous potassium fluoride and a bright green solution with aqueous potassium chloride. Explain. Okay, so basically if you just check aqueous copper sulfate, here in the coordination sphere itself the water molecule exists, outside SO4. Okay, now it is blue in color due to the presence of these ions, right? Next you can see whenever Kf is added, then it will form CuF4 2-. Okay, and whenever KCl is added, it is from CuCl for 2-. Okay, so both case it is weak field ligand. Okay, now water is replaced by F and Cl, right? That's the reason you will get different color. One is green, another one is bright green. Okay, for fluorine it is a little bit more than Cl, the field of the ligand. Then that's the reason, as water is replaced by comparatively weak field ligand, that's the reason there will be the change in color, a green precipitate for the fluorine compound and bright green for the chlorine. Okay, let's proceed. What is a coordination entity formed when excess aqueous KCN is added to an aqueous solution of copper sulfate? Why is it that no precipitate of copper sulfide is obtained when H2S gases pass through it? So basically whenever this copper aqueous solution of copper sulfate, it exists in this form, CuH2O whole for 2+. Excess KCN, if you add Cn minus, it forms this complex. Okay, CuCN for 2-, water is replaced with Cn. Okay, as a result of this, this particular compound is very stable. Okay, this particular compound is very stable because Cn minus is very strong field ligand. Okay, so this is the coordination entity that is formed out of it. This is the coordination entity. Okay, next part is why there is no precipitation. If you pass H2S gas, then copper sulfide precipitation will not be obtained because copper is a part of the coordination sphere, and coordination sphere it will not dissociate, right? Hence copper sulfide you will not get. Let's proceed. Okay, so that's it. So that's all about the entire coordination chemistry and D and F block that also we finished here. Yes, these many questions will be more than enough for your upcoming PU2 examination. So make sure if you have not subscribed this channel, please subscribe, click the like button and share with your other friends so that they can also get the benefits of this video. Thank you so much for watching.